Welcome back. So we'll continue our discussion on CFD, and that is the remaining discussion on CFD that will continue, and then we finally talk about the alternative wind energy things, and then conclude this. So now we talked about the conservation equations and all these things. Now here, what happens is that you have analytical equation, that means the physical problem. You apply your analytical approach, get the mathematical form, and then solve in the computer. So this mathematical form to form, this is what you apply the numerical methods. So now you see there is a range of different numerical methods: finite difference, finite element, spectral, Lattice-Boltzmann, finite volume, different methods. So the way you apply these methods, actually mathematically they are different. So the way you define or apply these numerical methods, you get different solutions in different ways. So eventually, you will get the same type of solution. So just to quickly talk about what finite difference does, it's there are advantage because it's a simple to do. It solves in the structure orthogonal system. But when you have a complicated geometry and all these things, then there is a problem with this method. Then you have finite element method, which can be applied to any realistic complicated geometry, but this is not straightforward. So you need to have a in-depth insight about this. The mathematical rigors are quite high. So obviously programming could be challenging, but this can be applied to complex problems and all this. But in fluid flow, finite element applications are not very popular. The third one, spectral method. This is again, it can be combined with FDMs and things like that. But this is relatively complex in comparison to standard FDMs. So implementation of complex boundary conditions could be difficult in spectral method. That's why it's not quite popular for wide range of fluid flow problem where you need a whereas this finite volume method, which is also, it has physical soundness, not as straightforward like FDM, but it can capture any realistic geometry by so commercial softwares are also mostly on based on finite volume method because this is quite popular in that sense, which allows you to solve the complicated problem. Now, in finite volume, what you do, you have this. So essentially, you get this del of rho phi del t plus rho ui phi minus gamma del phi by del xi dot nids, and this is q phi dot dv. So this is a source term. So this is for del of del xi equal to p dot. So this is how you convert. So this is your complete transport equation, which could be continuity equation. This could be continuity equation, momentum equation. So now what you can do is that this is how you get this system, and then finally that equation that we del rho phi by del t dv plus rho ui phi minus gamma del phi by del xi dot equals to u phi dot dv. So this is kind of, so this is what the domain where you solve this finite volume method. So these are, you can see this is how numerically, we can skip this. Essentially, any complicated geometry if you have, so there you can apply, and finally you get this you finally get this linear system. So this different numerical technique that you apply, they would eventually give you the linear system to solve. So that linear system, so this is probably nicely summarized in this slide. This is the omega plus C plus D minus this. So you have one unsteady term, you have convection term, you have diffusion term, you have source term, and then you have this time discretizations which you can do in terms of implicit or explicit, whatever. So essentially, so important aspect is that when I apply these numerical methods, the whole system turns to a linear system that I have to solve. This is where computer comes into the picture. But to solve the problem, I need to have, so like this is an airfoil geometry, this is some cylinder, you need to have grid. So simple grid is structure grid, or you can have unstructured grid, you can have block structure grid. So the way you so this grid generation is another challenging task, because when you have complicated geometry, then this grid generation becomes also complicated. And and also depends how you generate the grid. It that is kind of dictated by the kind of method that you are going to use, whether it's a finite difference or finite element or finite volume. So different methods allow certain flexibility, advantage or disadvantage over this grid. So grid has to be generated based on your tool that you have. Okay. And obviously, when you try to define a problem, your boundary conditions are the things. Just to solve any partial differential equation, you need boundary condition. So effectively, the solvers could be direct solver, or it could be iterative solvers, and then you can have other things to have convergence and things like that. Then partial differential equations, that you obviously define the order of discretizations and all these things, where you classify any generic partial differential equation, del x by del y plus c del 2 phi by del y2 del phi by del x plus e del phi by del y if phi plus g equals to 0. So that's any. So I mean, importantly, you have elliptical equation, there is a solution pattern, there is a parabolic, hyperbolic equations, but importantly, our Navier-Stokes equation. So if you look at it, the Navier-Stokes equation has different behavior. The pressure diffusion term is elliptic in nature, whether convection term is parabolic in nature. But then again, depending on the flow, this pattern changes or the behavior changes. Okay, so that is something very, very important, that uh, like you see this parabolic, elliptic, and mixed flows. So effectively, when we talk about the complete fluid flow problem, realistic geometry, this could be, now this is how you boundary conditions you could define in either you could have a Dirichlet boundary conditions where you specify the exact value, you could have gradient conditions or Norman conditions, or you could have mixed conditions. So these are the ways, or Robin conditions. Now the problems could be, you can have initial value problem, you could have boundary value problem. This is how you, now coming back to that, when you talk about the turbines and all these, important thing is the turbulence, because the whole flow around wind turbine is turbulent. So understanding of turbulence and turbulent models are very, very important. So what happens is that the flow which is turbulent in nature, when it passes over the turbine which is rotating, then try to get a proper load. Now here I would like to mention that this is where your simplified linearized model would lag, because it doesn't include turbulence and things like that. So that's sort where the full safety becomes useful, because it can use this turbulence model. So that turbulence models which are to use for the turbulent flows, you can use the correlation based system, integral equations, or Reynolds average Navier-Stokes equations, large eddy simulation. These are high fidelity one, but most of the engineering applications is done with this. Okay, RANS equation. So because turbulent has a property or nature that it say you have a large scale structure to small scale structure. You can see the DNS for realistic problem is quite expensive, even with the given computing resources for our problem of interest. Even today's date, that is very difficult. So that is why this is not expected. Alias is also expensive. So that is why I said engineering problem has preferred to solve using RANs. So what it does, so now this gives you the include as you go along this direction, you include more physics, but at the same time you increase the computational cost, you increase the complications. So DNS for realistic problems are still difficult today. LES possible, but primarily this box where the engineering applications are done using RANs. So there are a range of RANS equations. I mean, one can look at that in any textbook. There are two equation model, one equation model. I mean, they have their advantage, their disadvantage. Um, I mean, you can see their uses at different contexts, their behavior. So it's not that any particular model can be applied to any kind of flow. That is very difficult. So that is what I mean, usually not done. So depending on the flow pattern and how would you, I mean, this also list the strength and weaknesses of these different turbulence model. So that kind of gives you an idea of where to use what. So these are pretty standard. But there is another thing near wall treatment, because when we talk about, let's say, turbine, flow around the turbine, there would be boundary layer around those. So how you resolve that? So you need near wall treatment. So either use some kind of a standard wall function, non-equilibrium. So there are ways to treat that. So effectively, this gives you an idea that how one can handle those near wall treatment and things like that. But these are part of your turbulence modeling that one has to do that. So the standard wall function uses certain correlations, which are kind of one has to incorporate in the turbulence model. The non-equilibrium wall function uses certain correlations which one has to incorporate there. So what is that? Now these are enhanced wall function which also uses some correlations, but these are again to say that how much physics you would like to capture or not. That's what it turns into, and those are the things one and two. So these are some recommended strategy that one can, I mean, the first grid point, what could be there and how you do that. And based on that, certain recommended strategies there for different kind of problems. And also the boundary conditions for turbulence models are also there, because I mean, that's quite important, because when you talk about this turbulence model, so quickly you see this, what is your requirements, then what model and near treatments you require, then the procedures to follow which turbulence model and what not. So with that, if you look at the application, that is what we said, that in aerospace you see that flow around aircraft and all these things, these are really solving a large scale problem of nature. So when you go to appliances, you see that full spectrum of the domain of these appliances can be obtained. You go to automotive industries, so internal fluid dynamic behavior, external fluid dynamic behavior, everything has been kind of simulated. You go to biomedical applications, which is very, very emerging today's date, that medical device design and all these things where CFD is becoming a key ingredient at this moment. This is chemical processing industry. You go to HVAC, where heating, air conditioning, and all these things. This is hydraulics, where you see the dam, ship, and all these things. There are marine applications where CFD can be used. Oil and gas applications, power generation. This is where you have wind turbine is one of that, where you do this sports aerodynamics, which is another very interesting part, where you have this uh, applications to estimate this drag and all these things. So that this is how you can see this. These are some of the in-house applications that where you try to solve this kind of vertical axis wind turbine. You see how this rotating systems is handled. So so it gives you the complete picture of the fluid dynamic behavior and all these things. So this is another picture of the same thing. So here you see that a different kind of design. These applications could be for hydro turbine as well, but the important thing is that the whole rotating frame of reference has been taken, and considering these things to predict this. So this is another application, and this shows you again, this is a hydro turbine application where you see both. But the similar thing can be done even in the vertical axis wind turbine as well. This hybrid or variable pitch. Now, also interesting area is that AI/ML applications, because now there are a lot of site which has a lot of data, so the wind power forecasting can be an handy exercise, and one could do. But for that, one has to have certain data to tune their AI/ML based model, and then you can forecast that what could be the prediction in few minutes, half an hour, on our day, year. So long-term forecast, short-term forecast. So these are the things one can do. So where you can see certain models how they predict with the actual value, because in Denmark and Sweden there are a lot of wind farm. They collect a huge amount of data to support these kind of things. So in conclusion, this is a powerful tool, and this can provide a wide range of scientific applications and engineering problems to solve. But yes, you have to use it carefully, because it can provide meaningful result as long as you have set up the problem correctly. So there are certain funny things. You calculate, therefore you are. So you are fully conscious. mm, you think about you are the god, because tend to full the resources, risk to calculate a lot more and more, unsteady, understand few less, but that is not how things work. Important thing is that you may have a robust and efficient tool, but it is always important to estimate each point of view of the project if you want to obtain a result. So you have to take proper care of the whole thing. So computational fluid dynamics is essentially not colorful fluid dynamics. So you have to have a proper balance between these things. This is the scientist Roche who said that no one believes CFD result except one who performed the calculation. Uh, and then another great scientist who is no more said greatest disaster one can encounter in computation is not instability or lack of convergence, but results that are simultaneously good enough to be believable but bad enough to question. So all models are wrong, but some are useful. So essentially, what it says that you have to look at your competence, weakness of your stakeholder, the smart forecasting, so that you can have a good, robust tool, so that you can solve this kind of engineering problem. Okay, so that's how it gives you the perspective of the CFD, and how you can, or CFD as well as some CAE based tool which can be used for the design purposes. Okay, so now we'll move to the alternative concept. So we'll move to the alternative concepts, what is there, and to see how things are. So this is again going back to the horizontal axis wind farm. So you have an overview of that. You have the wind turbine connected at the offshore. Then you have a substation cables connected with that. This is again an image where offshore installations are done. So offshore horizontal axis wind turbine is a better wind sources, which we have talked because of very low roughness. Offshore construction have almost no restriction, limited variability of land. So obviously these are there. You can have high wind energy production, offshore installation only this much. So I mean these are some of the advantages that you have in the offshore installation that you can do. So typical loads that is acting, you can estimate all this. These are again, you see the blade passing frequency, rotor frequency. So these things we have discussed enough. These are again complete unit which are connected. I mean, this is the dynamics part of it. That is why we spend enough time to analyze that. But offshore wind turbine installations also can have, depending on the water depth, you can see the then this is 30 meter greater than 60 meter. You see that depending on the different depth, you can have different kind of installation. These are floating installations. So floating installations, how they're connected with the cables and things like that. So these are the structure which is visible above surface, but underneath there are other construction and all these things there at the seabed. And this is the spacing of wind turbine in site layout. So there are certain things that is coming out of this thing. This is a vertical axis wind turbine where Darius rotor. This is rotor. This we have seen also some of the application. Then uh, it's not large in size and all these things. These are Savonius wind turbine. This is a top view of it. So the interesting alternative concept that is going to be airborne wind energy. This is something one can think about it, how it is that. Now there is a comparison. First thing that a typical European needs 5 kilowatt because of electricity transport heating. This equals this much of 12 liters of petrol. One return flight of Europe to China consumes about this much of so. This is an electric heater. So this much of power requirement, you can see how much power requirement. But 5 megawatt installed capacity deliver an average about 1 megawatt. So this would be enough to cover all energy needs of 200 people. So what we can do, we can have a solar plant like that, or wind in North Sea, a turbine of 150-meter height. So this would provide you. Could we harvest wind power in high altitudes with less material? That is a big question. So that's the advantage. So what it is there, as we know, when you try to increase, I mean, see, this is a small turbine, this is a large turbine. Obviously, the power output of this power would be higher than power of this. So, but again, you have a long lever arm to large torque. So this is how the wind, this is the wind shear that is going to impact the whole turbine. Okay. And that can have difficulty. So the idea is that if you have a huge long tower, if you have big long tower, then it can get the fresh wind so that your power production increases. But obviously, the question is that structural stability. So idea is that in the, I mean, slightly away from the earth surface where the wind shear also gets little reduced, you have a clean wind or available, we can extract out the energy. But then we have to construct a long tower like this. So long tower is very difficult to build. At the same time, this will not have structural stability. But can we do something like that? If we connect this turbine only through a string, and then instead of the tower and extract out that energy, this is the, this is how we would like to do that. You get rid of the tower. There is no tower. Only the turbine is there in the air. So this is a very visionary ways to think about it. That the only thing is that the turbine is there. You connect with a string. So this is what the kite flies faster loop in crosswind direction. Very strong. So, but where could we generator be driven? So this is the crosswind kite power. The similar concept that so we can attach a small wind turbine to the kite cable, transmit the power. Then there are pros. It's light speed generator, propeller can be used to start and land. Cable needs to transmit power, generator. So that means the idea is that we put some turbine in the on air, um, and then so this was an artistic vision in 1992 that how these things can be done, and the cycle consists of two phases: power generation phase and then the retraction phase. Okay. Slow down kite, reduce force pull back line, all electric parts on ground and slow turning. So this is the concept. And as per the Lloyd formula, this is how you can have the power. And this is CL by CD. So that means if my CL by CD is high, this one can see the curve. This is the tension. This is power tension into rollout speed. And so maximum power reached at 1/3 of the wind speed. So this is what one can. Now, how fast does a kite fly compared to the real wind? So this is how you can estimate. Okay, and then find out the power out of that. Obviously, this is where you would like to. This is a 40 kilowatt per meter square. This, if you compare 1 meter square wind surface correspond to 250 meter square photovoltaic cell in solar power plant. So, but this size can produce 40 kilowatt. So this is an advantage that you have. Now, airborne wind energy vision. So you can replace tons of steel and concrete structure. So these offshore turbine at this today, which are the primary contributor for the wind energy production, but this could be replaced by this kind of. So you have this huge concrete structure, infrastructure building, and all this could be replaced by that. So what are the categorization? You have ground-based generation. That means the kite will fly and you connect with the cable, you have a ground or onboard generation. That means you have the turbine on the onboard, or either you can have soft wind. Fixed wing, you can have like this onboard generation, you have turbine sitting on the wing, you have soft wing, which is like in parachute. So the companies which are doing this, that Amaxi Power in Netherlands, Makani Power in California, Kaisels, Hamburg. So these are the industry which are kind of, there is a book there, one can look at this airborne wind energy. So for simple plane attached to a tether, you have 20 differential states, and then you connect with the tether, and then it goes in a loop, or it goes in a particular around the system. Finally, you extract out the. So this is what in a high wind picture, that rotation to power orbit. So they are going to fly this thing. So this is another flight experiment in Leuven, that what is the these tether planes follow certain paths. So the flight path estimation is important, and then one could have a dual kite system. So then you have a main tether, then you have a secondary tether, so that it can stabilize each other, and they go in a cyclic path where you extract out the energy. So this is quite interesting concept, and this is an example of dual kite system. You can see this is one here, this is one here, which is connected, and the cable is connected there. So there are Amoxipar is a startup from TU Delft, about 40 permanent staff. They are venture capital. This is pumping cycle to harvest wind power. This is another capsule start of this. This is again going to the seabed to have this kind of things which are flying there so that you could. This is soft kites with the ground-based generator. That means it's connected and you have a ground where things are the one generator. This is an example of an sky cell that it is in 2001. So that means this soft structure is connected to the cable where the ship is sailing. So these are some fun things at riverbed where you can see where ground-based generator can be used. Now this is an example of rigid wing based generator. This is an Makani power turbines on board. So you see these things which are there. This is how, I mean, this design could be optimized or it could be kind of, this is connected with the wing. How, so when the things are flying, this is Makani Power 600 kilowatt utility scale. This was in April 2015. So they have kind of tested it, and these are some of the pictures in 2017. These are the system tests they had where they wanted to, and this is the picture you can see when this is flying, and you have this onboard turbine generators which are doing this job. So what it does that the airborne wind energy, quite promising concept, which you can utilize the wind power available at the clean air. Obviously, some nonlinear control optimization, all this. So it could have a different way onboard ground-based generator, soft wing, fixed wing. But this is a very handy concept, and this is kind of connected with the UAV kind of things, where you can have these turbines. And I mean, obviously, these are talking about some futuristic technology and that one could have. That pretty much, I would say, concludes the complete discussion on this wind energy. So we started with basic fluid mechanics, then went into the discussion of energy scenario, energy perspective, horizontal axis wind turbine, vertical axis wind turbine, then wind turbine, both horizontal and vertical axis wind turbine aerodynamics. Then we talked about the dynamics, which is more like a structural for design purposes. And then finally talked about the CFD perspective and the alternative concept like airborne wind energy. I hope. Thank you very much for listening and attending this. Thank you.